Oh, my name is Andrew Menches, and today we're going to be talking about magnetic dipole moment estimation from near-field measurements via AI modeling using stochastic gradient descent. So the topics we'll be going over is a brief introduction to the problem, some background on the motivations behind magnetic testing, some of the existing approaches, AI and machine learning techniques that we will be using in our new approach, and then the results of our testing. With the rising popularity of CubeSats, the need to determine the magnetic field of a spacecraft again becomes more of an issue. We will show a method to estimate the magnetic dipole moment of a spacecraft from near-field flux gate magnetic measurements by using techniques developed for machine learning. This method can be used in laboratory settings with minimal equipment, and the benefit to this method is that the measure of error is directly known as the fit is determined and does not need to be separately calculated after the estimate is completed. It can also be extended to ensure optimality. So some background and motivations behind the magnetic testing. When scientists first started developing Earth orbiting spacecraft, it became very important to determine what the effective dipole moment of the spacecraft was. When an object is orbiting the Earth, the magnetic field of the Earth will interact with the magnetic field of the object, forcing that object to rotate and realign with the Earth's magnetic field. This became a major issue for the attitude control systems on the Earth orbiting craft. The spacecraft would have a magnetic cleanliness program in place to limit the amount of permanent magnetic field residing within the components of the craft. There needs to be some number of ferromagnetic components on a spacecraft, so not all permanent fields can be avoided. Engineers would attempt to measure the effective dipole moment of the spacecraft. Once they're able to determine that, they could then magnetically balance the spacecraft, much like balancing a tire by placing the correct amount of weight on the correct spot of a tire. You can place a permanent magnet on the correct strength and the right spot on a spacecraft to effectively balance out the magnetic field. This would prevent the spacecraft from spinning uncontrollably while in Earth's magnetic field. By minimizing the amount of unwanted torque acting on the spacecraft within Earth's magnetic field, less energy would be required to counteract this force. As the power systems for spacecraft became more robust, the need for such strict magnetic cleanliness programs fell by the wayside. Developments within attitude control systems allowed for the use of items like reaction wheels and magnetic torquer bars to effectively counteract the amount of torque on the spacecraft while being able to power and operate onboard science instruments. Although many missions still require a strict magnetic cleanliness program, even for these subsystems, that is not always the case. The emerging standard for Earth orbiting satellites and lunar satellites appear to be CubeSats. Satellites are much smaller than the typical Earth orbiting platforms that are developed by NASA. These CubeSats are popular because they are cheaper to build and launch, and with such a small size, clusters of CubeSats can be launched from one payload. These smaller satellites reintroduce the problems of the past with respect to the interactions of the magnetic field. The small satellites quickly run out of room to place onboard magnetometers with respect to the science instruments that we would like to pack into these small satellites, and that can affect the permanent magnetic field of the satellite. Some of the existing approaches that are used for determining the magnetic dipole moment of a spacecraft. There are a few different methods that have been employed to try and measure the magnetic torque of a spacecraft. In the Apollo days of the NASA space program, the engineers attempted to directly measure the torque of the components on the spacecraft. Items were placed on a turntable at the center of a Braun-Brett configuration Helmholtz coil, and the magnetic field was measured by a triaxial flux gate magnetometer. By applying the external magnetic field that would counteract the Earth's magnetic field, a very stable environment can be developed for measuring the magnetic field of the item under test. In the early 1970s at NASA Goddard Space Flight Center, William Eichhorn developed a method that would attempt to measure the magnetic dipole moment of a spacecraft using spherical harmonic analysis. This method would rotate the test article about the z-axis while recording the B field measured by the magnetometers, placed at specific distances from the spacecraft. The fields would effectively be mapped onto a sphere, and a Fourier transform would be performed on the data. This method is similar. A method similar to this was recently proposed by Louis et al. This method proposes to use magnetic gradient tensor data. It is resistant to noisy time-varying magnetic fields seen in laboratory environments. Other attempts have been made to try to perform the Monte Carlo best fit, where an effective dipole would be randomly oriented with randomized magnitude, and the field would be calculated. Mean square error would be determined for each randomized orientation, and the best would be saved off. There are several problems with these approaches. The direct measurement method is only effective for larger items, and there is a moderate margin of error. Spherical harmonic analysis appears to suffer from errors that appear in the specific orientation of dipoles with reference to the point of measurements. And the Monte Carlo method suffers from the search taking an unspecified amount of time to determine the moment if one can be found. All of these issues are exacerbated by the necessity of taking the measurements within the near field. The fall off of the magnetic field is so sharp that it necessitates taking measurements very close to the spacecraft. To make the problem even more difficult, these types of measurements require a magnetometer with a sensitivity of a nanotesla or less. Typically, a good flux gate magnetometer is sufficient for this task, but with these types of sensitivities, it is very easy to have interference within your measurements. In order to achieve the low noise necessary to do these types of measurements, many facilities employ either a Helmholtz coil or a Braun-Breck configuration for a Helmholtz coil to actively negate the effects due to the Earth's magnetic field and outside influences. So some of the applied machine learning concepts that we will be using here. Regression models have likely been used the most out of all machine learning techniques. The output of a regression problem will generally be a continuous variable, as opposed to the discrete variable output of a classification model. Clustering is an unsupervised machine learning technique that will attempt to classify data that is associated with other similar data. There will be some metric that is used to determine the distance between data items and label those items that are close together to be within the same group. K-nearest neighbors is the most common clustering algorithm. Perceptron neural network. The perceptron is a singular unit of the neural network or an artificial neuron, where they have a linear function associated with them, where W is the weight associated with the connection and B would be the bias of the neuron, and X is some input. Both W and B are learnable parameters. Typically, the neurons have an activation threshold, which will give them some form of nonlinearity. When no activation is applied, it is considered regression. Deep learning. The field of deep learning is currently the most active area of research in AI and machine learning, and there is good cause. It has been shown that deep learning can potentially learn almost any data set given enough data and the appropriate model design. Deep learning consists of layers of artificial neural networks represented by a tensor of weights that can be biased and activated to predict some value. During training, this value is evaluated with a loss function against the ground truth. The forward pass creates calculation for prediction, but the back propagation combined with node activation is what actually gives the model the ability to learn. Deep learning is generally defined by having more than one layer of neural networks. Stochastic gradient descent. In machine learning, the goal is to minimize the loss of some function that calculates the error between the predicted values and the ground truth. In this way, the machine can begin to narrow down the predicted solution space into a set that is closer to the true value the model is trying to predict. Gradient descent is a method to determine the minima of a function. Taking the gradient of the loss function, we can determine the slope of the function and take small steps along the gradient towards the minimum value of that loss. The learning rate will determine how large of a step is taken in the direction of the minima of the function. If we adjust the weights of the machine learning model during the backpropagation phase by these small steps, we can achieve this minimum. Given the goal of this algorithm is convergence on this minimum, and the data sets can be extremely large, it can take quite a while to converge if the data is fed into the algorithm in sequential order. It has been shown that convergence can happen more quickly if the data is shuffled and then fed into the algorithm. This technique is known as stochastic gradient descent. The new approach that we are taking to determine the magnetic dipole moment. Techniques applied to machine learning can also be applied to the problem of magnetic dipole moment determination. We can combine the near field measurements of a spacecraft that is rotated about the z-axis with stochastic gradient descent in lieu of Monte Carlo to more quickly determine the effective dipole moment of a spacecraft. Here we can see the input to our neural network will be the position vector of the observer, and the output will be the B field in that position vector. The loss function will be the mean squared error, and we will set the learnable parameters of the neural network to be the magnetic moment. This slide shows what a typical test setup would look like. The test article is centered at the origin, and triaxial fluxgate magnetometers are positioned directly in line with the center of the test article. The first magnetometer is placed 1 meter from the origin, and the subsequent magnetometer is placed 33 centimeters away from preceding magnetometers. A measurement is performed in this configuration. The test article is rotated by some set angle in the XY plane, and the measurements are taken again. This is repeated until a full rotation is made. This test setup, as seen here, would generate 48 individual points of measurement. We will constrain our analysis on solving the problem described by this test setup, where the multipole systems we are trying to determine the effective dipole moment for will be bounded within the volume of the test article, meaning the dipoles within the multipole system will be within the field of rotation described by the magnetometer measurements as the test article is rotated for a full revolution. The measured field data for a dipole at the origin with a strength of 0.1 amp meters squared in the x-axis, 0.2 amp meters squared in the y-axis, and negative 0.6 amp meters squared in the z-axis can be seen in the other plots. This is the type of data along with the position data that will be fed into the machine learning model to try and solve for the effective dipole moment of the system, where each point in the plots are points of measurements taken by the magnetometers during the test. To begin to develop the network to solve this problem, we will need to generate some data sets to feed into the machine learning model. We can develop a separate application to generate our data sets. This application will need to allow for the inputs of an arbitrary number of dipoles at specific locations with either using specified or random values in the X, Y, and Z components of the moment. We can then use those moments to calculate the B field and radials about the origin. In order to develop the simulator and the regression model, we will need to be able to calculate the flux density due to the dipole moment at an arbitrary point of observation as seen here, where mu sub 0 is the permeability of free space, which is equal to 4 pi times 10 to the negative 7th. The point of measurement or observation point is referenced as x sub O, y sub O, and z sub O. The point where the dipole moment exists is referenced as x sub I, y sub I, and z sub I. In developing our AI solution, we will simplify the problem by solving for a single dipole moment centered at the origin. The artificial neuron functions in our neural network will not be the linear function of y equals wx plus b, but instead the equation for calculating the magnetic flux density, or B field. The equation shown here is in vector notation. We can use the mean squared error as our loss function and stochastic gradient descent to optimize the minimization of the mean squared error. So on to the results. Baseline testing was initially performed on a trivial test setup where the simulator generated the B field of 3 dipole moments located at the origin. This table shows the initial set of configurations. The tests consisted of a wide range of dipole moment magnitudes to test the accuracy of the method. The table shows the moment that the simulator generated B field values for, as well as the accuracy for the model's prediction of the field. The mean squared error is listed to show how well of a predictor it is for model fit compared with accuracy. The model was trained on 100 epochs of data with a learning rate set to 1000, with the moment position being held at the origin. There are a few things to note from this table. First, the accuracy of the method on the trivial problem appears to decrease as the moment values increase. This can be addressed by adjusting the learning rate for the model. It can be seen that the accuracy remains extremely high in the worst case, with the model being accurate above 99%. The next set of tests was to verify the non-trivial problem. This is when the dipole moment is not at the origin. This becomes non-trivial as no single dipole moment can accurately recreate the near field of any arbitrary multipole system with sufficient complexity. There is expected to be a certain amount of error between the near field and the assumed far field of a true dipole moment. For the non-trivial testing, the simulated dipole moment was held constant and the position of the moments were shifted along a sphere with a radius of 0.6 meters to 0.001 meters towards the origin. The moment was chosen to have the components of 1 amp meter squared in the x-axis, 2 amp meters squared in the y-axis, and -6 amp meters squared in the z-axis. This provides a range of values that are within a reasonable range for real-world testing of spacecraft. The model was trained on 100 epochs again. It can be seen that the results are as expected. As the dipole moment becomes more difficult to mimic with a single pole system, the mean squared error increases. This method does appear to find a minima of the function, and although it does not show up the optimal solution of the non-trivial problem, it does solve the problem. Conclusion. The method provided here shows how to apply machine learning models with stochastic gradient descent to solve for a magnetic dipole moment. It can be seen that the method is extremely accurate for the trivial problems and can still be moderately accurate for the non-trivial problem. It would be relatively easy to extend the method to prove an optimal solution. In theory, any sufficiently complex B field generated by a non-trivial multipole system can be replicated with enough properly oriented moments at the origin. The machine learning model can be modified to have an arbitrary number of corresponding moments for weights. The number of moments for the machine learning model would contain the number of moments the machine learning model would contain would be specified on instantiation of the model. Just like k-means clustering, the optimal number of moments needed to correctly replicate the arbitrary B field is unknown. But using the same method as k-means clustering, we can prove optimality by fitting models with increasing number of poles until the slope of the mean squared error of the overfit model begins to move at a slower rate of change. The resulting weights of the model within the optimal fit can be summed along the x, y, and z axis to determine the optimal dipole moment of the multipole system. Future work will be to develop these models. It would also be possible to extend this model to solve for positions and magnitudes of a multipole model where the dipoles are not located at the origin. This could be useful for trying to understand the magnetic composition of the article under test. It would also provide the benefit of positioning the onboard magnetometers where they will be subjected to the least amount of magnetic noise. This knowledge could be useful for any other magnetically sensitive science instruments on board the satellites as well. And this is the team that worked on the paper. Myself, Andrew Menches, and Dr. Bharat Rawal. Thank you very much.